So I happened to be sat at the back in the last talk and overheard Alexander's disdain for beamer slides. So I apologize, another one. I would like to come up with something as flashy as Josh's or James from yesterday, but as they will tell you from working with me for so long, while I may not exactly be a Luddite, I'm never quite current either, so here we are with yeah, I'm going to talk a little bit about some techniques to do with tensors, which have really been developed over a long collaboration with James, and more recently with Josh Maglione as well. And while I was thinking about what I was going to cover in this talk, and thinking about all of the different kinds of equivalences of tensors that we had sort of developed over the years, you know, things that are the same up to change of basis, you know, some themes that we heard about yesterday in yesterday's talks. We developed quite a lot of vocabulary over that time, and so I was trying to, in the overarching theme of these lectures or tutorials, I was trying to come up with a name which sort of captures all of those things. And from conversations with Josh Grochow a little while ago, I've heard him use the word equivalence quite a few times, and so I thought, well, I'll call these things tensor equivalence problems. And then I was sort of dismayed yesterday to find out that these are no longer to be called tensor equivalence problems, rather more isomorphism problems. Whatever we want to call them anyway, that's going to be sort of in the background of these talks anyway. It's going to be one of the motivations really, is to really provide some kind of tools which can help you study tensors, and in particular help you attack those kinds of problems. So I'm going to be sort of treading over some ground that we certainly saw yesterday in James's talk, in Josh's talk, a little bit in Josh Grochow's talk as well, and also a little bit from Alexander's talks. In particular, the dichotomy that Alexander mentioned at the beginning of his talk yesterday, the red-green dichotomy. You'll notice that I wore a rather snazzy shirt today. This was in part an homage to Josh's wardrobe choices yesterday. But also, you know, the little green specks and red specks are sort of, you know, indicative of my the hats that I'll wear today. I'll try to talk from both a red and a green viewpoint. And the other reason, of course, is that I only really brought one shirt with me, so this is it. Yeah, so we'll talk a little bit about, as I say, I'll talk a lot about tensors, but from a practical point of view, also from a theoretical point of view. There will be some complexity results. There'll also be some algorithms. I'll kind of mention these things. I won't really dwell on either of these things. What I really want to do is to try to give you a sense of what some of these algebraic tools can do for you. And so to just kind of echo what James said earlier, do please stop me. I'll try to go at a somewhat sedate pace, but if you find that I'm going too fast or whatever, or if questions arise as we go along, do please kind of interrupt. I have been scheduled for 2 lectures, so if I don't get to where I was going to today, then I can prevail upon you on Friday to kind of pick up where I left off anyway, so it's no big deal. So let's begin with a little bit of notation. Again, this is kind of reiterating some notation that you saw yesterday in a couple of different talks. So we're going to use this, in particular, this kind of bra-ket notation. The bra is going to be an interpretation of what we'll call a tensor as a multilinear map, and then the ket is going to be evaluation of that tensor at some fixed element of the frame. I will say that in these lectures, just to kind of keep things fairly simple, and so I don't have to keep giving you different hypotheses for different things that I'm going to say, let's just assume throughout that I'm going to talk about bimaps today. Some of the things that I'll say will apply to tensors of arbitrary valence, but we'll just stick with bimaps. There's kind of enough to say about that particular context that we won't lose too much. I'll also say that because I'm kind of interested in efficient computation, I'll just assume the field here is a finite field throughout as well. It's just a field of p to the k elements. But again, you know, some of the things that I'll talk about today do apply in more generality than that. And, you know, to echo what Alexander said as well, I'm happy to talk to anybody about any of these things. If you want to talk about things that are more general than I'm talking about on the slides, then I can certainly do so throughout the next couple of weeks. Great. So, a little recap of some of the themes from James's talk yesterday, operators on polynomial rings. So we're going to fix this capital omega to be the direct product of the things that operate on all the different coordinates of the tensor. So I'll use the letter omega. I think that's a little different from what we were using yesterday, but it doesn't really matter. And omega is going to have these coordinates, omega 2, omega 1, omega 0. And slightly differently from Josh's choice yesterday, I think he used u cross v into v, u cross v into w. I'm going to keep hold of the indices here for quite a while until we start adding a little bit of symmetry to the situation, and then I'll probably revert back to sans subscript. But it's sort of helpful to kind of keep track of where these operators are acting if we keep the subscripts for a while. So yes, so we have this action of the polynomial ring in three variables, x2, x1, x0, acting on the tensor space by extending the action that you can see here. I don't know why I'm pointing at that, I should be pointing here. So you can sort of extend this action. So if you have a polynomial you can sort of write in this way, then you can act on the tensor space in this fashion. So again, this is something that you saw in both James's talk and Josh's talk yesterday, so I won't dwell too much on that.
That 0 was in the superscript, the one in front of the T in the sum.
Oh yeah, it looks like it, doesn't it? Yeah. I'll change that.
Yeah. Make sure nobody thinks you're multiplying by 0.
Well, that would make the annihilation very easily. Yeah, thanks, James. Yeah, I'll correct that. Great. So yeah, so if you remember, there was this set that James introduced in his talk yesterday, this annihilator set. So for a fixed omega, you can define an action of this polynomial ring via the element omega, and then the annihilator related to omega of this particular tensor, all of the polynomials for which, when you evaluate at that particular omega, they make it vanish. Okay. And so James noted this particular set, which is called ZPT yesterday, of all of the elements, all of the operators for which the set of polynomials lies inside that annihilator. And he mentioned that this is kind of a difficult thing to compute in general. And we'll kind of, hopefully, over the course of the two lectures, we'll sort of see why that's the case. So we'll see sort of examples of things that are easy versus things that are hard, and kind of drill down into the things that are hard. So I'm not going to talk about this at all in the generality that James mentioned yesterday. There was an entire correspondence theorem, if you remember, sort of a ternary correspondence between polynomials, tensors, and what's the other thing? Operators. Yeah. So we're not going to go into that correspondence at all, but we're going to talk about specific sets of polynomials here. And I've just given you a few examples, and you may remember these from yesterday as well. So the polynomial x2, x1 minus x0 is a sort of equivalence, right? This is if you like, the isomorphism that Josh was talking about, or one of the isomorphisms that Josh Groshar was talking about yesterday. We'll call these things autotopisms. This is one of the elements of vocabulary that I mentioned, that is some form of equivalence of tensors. If you take these three polynomials, x2 minus x1, x2 minus x0, x1 minus x0. If you take those as a set together, then you get what's called a centroid. Okay? And similarly, if you take this nice polynomial that, again, you may recall from yesterday, x2 plus x1 minus x0, you get a set that we'll call derivations. So we focus on these things because they have additional structure. These two things are rings. We'll study this one today for sure. This one, as you may recall, is a Lie ring. This was sort of, I think what James was trying to impart yesterday to a great extent in his talk is that this is sort of the natural object, natural linear object to look at these derivations. We'll maybe say something a little bit about this on Friday, but not so much today. And then this one is really, if you like, the guiding goal of the next couple of lectures is to try to develop techniques that will enable us to calculate or to construct this, what turns out to be the group of autotopisms of a particular tensor. Okay? This turns out to be a hard problem. We've heard Josh Groschau talked about this being a hard problem yesterday, but we'll try to develop some tools that are kind of easy to calculate, but will shed some light on this problem. Okay. Any questions so far? Right, so as I mentioned before, a couple of these sets that have arisen, that arise when you look at these zero sets are algebras and groups. And so I'm going to be talking a little bit about algebras and groups, and so it seemed to make sense to talk a little bit about computing with these things. And from Alexander's 2 lectures yesterday and today, you'll have learned a little bit about this, right? Quite a lot about groups and a little bit less about algebras. But let me just give you some of the basics that we'll assume here. So we're going to assume, first of all, that these things are given to us by generators in both cases. They're going to arise naturally as matrices, and so we're going to specify the generators as matrices. And so groups, for example, are going to be given to you by some collection of matrices X from the general linear group of some dimension over a finite field F. And this is the notation that we tend to use when we're talking about groups generated by sets, just angle brackets X. For algebras, how do we define this? So what do we mean by an algebra generated by a set? Well, it's kind of pretty much what you expect it to mean. You start multiplying together these matrices, and then you can sort of look at combinations of them as well, linear combinations of these things. Perhaps the accurate way to describe this is that if you look at the monoid generated by X, I should point out, by the way, that we're going to be talking about associative algebras only today. And in our associative algebras, we're always going to be talking about unital associative algebras. So in addition to the element X that you may generate by, we're always assuming that the identity is in there as well. So if you look at the monoid generated by X and look at the linear span of this, this is what gives you the algebra. Okay. So very quickly, modules. Again, from Alexander's talk this morning, you may recall some talk about modules for both groups and algebras. So I guess the theoretical definition is that you've got a homomorphism from your algebra into the endomorphism ring of a module U. And so you may recall from in our computational model, we're going to assume that algebras are given by a fixed generating set. And so we're going to specify a module by the action of that fixed generating set on the module, right? So if you want to specify two different modules, you're assuming that you're going to specify the action of the exact same generating set on those two modules, okay? So for example, if you have a matrix algebra that's specified by a set of matrices X, then X is you assume that X actually is your prescribed generating set, and then X itself would define the natural underlying module, which would just be the vector space of the dimension of the algebra. If you're given two modules that are specified by two different generating sets, let's call X1 through Xn, Y1 through Yn, then what we mean to say that they're isomorphic now, again, going back to Alexander's talk this morning, what we mean by that is we've got a common conjugating matrix that takes you from one sequence of elements to the other sequence of elements. And once again, this is because, just to reiterate, this is because it's the same, you're assuming it's the same sequence of generators that you're using to define the two modules. So they have to take them element-wise to each other, this conjugating matrix. So there is, of course, a slightly more general problem, well, quite a lot more general problem that you might ask, which if you're used to kind of thinking about module isomorphism, but not necessarily used to thinking it from a computational point of view, say using the metax, then you might think about module isomorphism in a slightly more general way. And this is something that we'll call perhaps module similarity using this language. And it relates to problems to do with algebras that we'll come to next time. Okay, so this is actually, turns out to be a very hard problem. Josh Groschau kind of mentioned some aspects of this problem in his talk yesterday, but we'll come to it next time. So sort of the moral is that today is sort of the easy stuff, if you like, and then next time is going to be how do you apply that easy stuff to the harder stuff. So this, as Alexander mentioned earlier today, is an easy problem. You can solve modular isomorphism easily. He did mention, if you were kind of paying close attention today, you will have noticed that he talked about just the irreducible case, right? So we've got an irreducible action. It turns out that there is a deterministic polynomial time algorithm for modules defined over any field at all, not just finite fields. And so this is a problem that can, in fact, be solved in much more generality. But I want to mention here the power of the metax, just how useful it is. From a practical point of view, it underlies pretty much everything I'm going to say today. Right? So all of the implementations that exist in Magma and GAP, they're all going to use this powerful machine that Alexander talked about a little bit earlier. Great. So I think that's the basics. Let me move on then to the centroid ring. So what is the centroid? So it was, if you remember, it was defined by this trio of polynomials, x2 minus x1, x2 minus x0, x1 minus x0. What these polynomials are trying to capture, of course, is that anything that satisfies them is going to be a global scalar for that particular bimap, right? So it means you can kind of move things around between all coordinates, all three different coordinates. And so in particular, the centroid of a bimap T, T is going to be bilinear over that centroid, if you will. Okay. A couple of other things are introduced at this point. The radicals of a bimap, I'm not too sure anyone's kind of talked about that in the talk so far. So the radicals are pretty much what you think they would be, but there are two of them here. There's one in the 2 coordinate and there's one in the 1 coordinate. So these are all the things that if you take all of the vectors, if you will, in U2, I'll just point to it, these are all the vectors in U2, so that if you take everything in U1 and apply the tensor to U1 and everything, U2 and everything in U1, then you vanish. Okay. And similarly for U1, there's another radical there. And so we're going to say that the tensor itself is non-degenerate if both of those sets are 0. And for the, I suppose I can also mention this other thing as well, that if the image, if you like, of the tensor is all of the codomain, then we'll say that the tensor is full. Okay. So in all of the problems that we're interested in over the next couple of lectures, it's a fairly routine affair to, if you don't have a fully non-degenerate tensor, and the problems that you're interested in, you can reduce to a fully non-degenerate tensor without too much trouble. I won't go into the details of how that happens, but if you just take my word for it that it does, and for the sake of argument, we'll assume from now on that a tensor is fully non-degenerate. Okay? So here's a nice little lemma that if you do have a fully non-degenerate tensor, then the centroid of the tensor is a commutative ring. So this is a nice property. It's maybe not too surprising given the name of it perhaps, but this is a nice fundamental property of the centroid. And moreover, it acts faithfully on each of the different coordinates. Okay. So just to reiterate here, another way of saying what the centroid is, we've got some equations here, we've got some properties. Another way of saying what the centroid is the largest ring R over which the bilinear map is really it's an R bimap, if you will. Okay. So we can in fact rewrite the tensor as a tensor over that thing, and that's usually a useful thing to do. So let me start with kind of a toy example that kind of illustrates this. So here's a very elementary tensor. I guess I didn't really talk about computational models, did I? But let me say a word about that first. So you notice here that I've described this tensor by means of 2 matrices. Okay. So why is that? They're both 4x4 matrices, and the codomain is f3 squared. So one way that you could represent this tensor is by taking a little f2 vector, if you like, or an f3 squared vector in each of the different coordinates. Another way would be to kind of slice it, if you will, kind of slice it depth-wise, and then write down just 2 matrices that are kind of the basis, if you will, of your tensor. So in this particular example, I've chosen to do the latter. I've just taken 2 different matrices. One of them, we've just got 0 with the 2x2 identity matrix in the top right-hand block. And in the second matrix, we've got this little fairly simple looking matrix, 0, 1, 1, 1. And if you kind of roll up your sleeves, they don't really have any, and just kind of write down what the equations are that kind of determine the centroid, then you can fairly quickly calculate that the centroid here is isomorphic to this. It's basically just this kind of duplicated down the block diagonal. And because this is an irreducible 2 by 2 matrix over F3, then the enveloping algebra, the algebra generated by this thing, is just going to be a field F9. Okay. So what this is really saying is that rather than think about this as a 4 by 4 tensor over F3, what you should really do is to think about it as a 2 by 2 tensor over F9. Okay. Okay, so it's not really a big deal on this example, but you can imagine that if you're looking at much bigger examples, this is a nice saving that you'd want to take advantage of immediately and write it over the correct field, if you will. So in this particular case, as you can see, what we should be doing is just representing this by a single form, 1, 0, 1, minus 1, 0. So just a little alternating form over F9. This might be a nice time to mention, in fact, that Josh has implemented this particular aspect in Magma as well, right? So if you're given I think you mentioned a number of tools in your demonstration yesterday, Josh. And one of the things that this suite of functions can now do is if you're given a tensor, you can calculate the centroid easily enough, but then there are also functions that will rewrite that tensor over the correct field, which is really quite nice. All right, any questions so far? All good? So I thought I'd show you this anyway. This is quite a cute little thing. How is it that this centroid is commutative? And this is something that's referred to as the 3-pile shuffle. I thought this was quite amusing when James first mentioned this proof to me, the 3-pile shuffle. But it really sort of illustrates why you need these 3 different components. Soon we're going to move on to some rings where we kind of restrict, and we're not talking about all 3 components at once. We're going to restrict and just focus on 2 of them. And this really illustrates why this is kind of a nice ring and the others aren't so nice. So just kind of following these equations, I thought it might be just kind of useful to get used to the definition of the centroid a little bit. So I'm going to assume here that we've already shown that the centroid is in fact a ring represented faithfully on each coordinate. This is not a hard exercise, you can do it yourself. So in particular, omega pi is going to be in the centroid, and because it's in the centroid, you can pull out that second scalar, if you will, to the front of the tensor here, and write this as omega pi 0, which of course just kind of breaks up in this way. And now the idea is that you kind of feed these 2 scalars back in, but to different coordinates. And this allows you to just kind of change the order of the order in which the operators act. And then we end up here, because it's faithfully represented on the second, or it's faithfully represented on all coordinates. In particular, it's faithfully represented on the second. And so omega pi equals pi omega on the second coordinate, therefore it's commutative. So that's sort of quite a nice little exercise. Great. So let's talk about the adjoint ring then. And I think I'm going to like 2:45-ish, so okay, yeah, about half an hour. Great, so we're going to take our bimap T again, and this time we're going to associate to it 3 different rings. So you may remember there were 3 different polynomials in the definition of the centroid. We'll take each of those things individually and look at the ring. Well, we'll look at the objects that you get when you kind of focus on those particular things. I'm going to focus on the middle scalars here. So I'm going to be looking at this polynomial x2 minus x1. And if you write out what this means, the polynomial equation gives you this sort of equation, this kind of adjoint relation. We've seen this a few times already in the talks. And again, I think James alerted you to this yesterday, that somehow associative rings are kind of anomalous in all of this and unnatural in some way. And so to make this into an associative ring, we have to make sure that we act in the second coordinate by the opposite ring. Okay? So this is the action that you would get here in the omega 1 coordinate. So omega times pi, applied to u1, you switch the order of the operators. And if you do that, then what you end up with is an associative ring here. So some properties, just to record that fact, that it does indeed rely on the opposite ring. So what is this adj really anyway, this ring of adjoints? It's the largest ring over which the algebra is A midlinear, okay? So what does that really mean? It means that we can kind of tensor over that algebra, right? So it's the largest ring A over which the bimap T factors through the tensor bimap A2 tensor A1. And what that means is that there is a linear map, which we call T hat here, that goes from the tensor product to the codomain space, satisfying this equation that you see right here. Okay. And I've just made the remark at the bottom here that this is, I'll take up this point of view about the adjoint algebra on Friday when we talk about a certain technique that we can use to try to attack the orthotopism problem. Remember, that was kind of the overarching problem that's kind of motivating us here. If you like, the theme of these lectures is how can these linear tools help you attack hard problems like that? And so we'll get back to that on Friday. And I'll remind you of this at the beginning of the lecture on Friday, but this is a perspective that we'll take advantage of when we return to that. Okay. So we've seen some commutative rings, we've seen some associative rings. Obviously, if we want to actually use these structures, these are nice structures, if we want to use them to help us with computations, then obviously we're going to have to be able to compute with them. Okay? So I'd just like to talk for a little bit about computational properties of rings. So I'm fairly sure that I'll be saying a lot of things on this slide that people know about already. What this slide basically displays is the standard Artin-Wedderburn theory of associative algebras. And it dates back to sort of the early 20th century. But let me just summarize what it basically says. So first of all, if you're given this algebra A, you can calculate its radical. The radical you can think of as the intersection of all of its left ideals. You can also think about it equally as the intersection of all of its right ideals. That turns out to be kind of an important thing a little bit later on, so I can store that piece of information. But if you intersect these, all of the left ideals, the set of left ideals, or the set of right ideals, then you get this thing called the Jacobson radical. Every algebra has a decomposition into the radical together with a semi-simple part. And this is a rather idiosyncratic name probably for what you get here. This is sort of a radical semi-simple decomposition, as you can see. I've chosen to call it here a Wedderburn decomposition. This is mostly, this kind of mostly grew out of algorithms that James and I sort of developed over the years to kind of distinguish it from another kind of decomposition that we'll see a little bit later on. So it may not be sort of historically exactly the right thing to call it, but anyway, that's what it ended up being called, the Wedderburn decomposition. So it's just a decomposition of a given algebra A into radical together with semi-simple. And then, of course, you can take this semi-simple algebra and you can further decompose it into its minimal ideals. And in this nice associative unital ring case, the minimal ideals are pretty well known. They're all going to just be matrix algebras over some kind of extension field of the field that you're given. Okay. So that's all fairly standard theory. Let me just talk a little bit about the algorithms. So the first algorithms really were due, I believe, to Laios Ronyai. Certainly the first paper that I saw that kind of talked about the structure of these algebras, how to actually access the structure of these algebras. This is a paper that I think came out in 1990, Journal of Symbolic Computation, was it, I think? Over the course of the 1990s, the algorithms, he basically kind of gave some nice theoretical ideas for how to go about computing these things without thinking too much necessarily about practical implementations of these things. He was really trying to establish a sort of a polynomial time theory. Over the 1990s, though, numerous authors, I've mentioned a few here, but I'm guessing there are a few more who contributed to this, but Eberle Giesbrecht, were two authors that contributed to these improvements, and also somebody that was mentioned, I think in Alexander's talk this morning, Gabor Ivanios, also contributed quite heavily, starting with his PhD thesis, to the development of algorithms for these things. And I'll mention as well that there are implementations, certainly in Magma, that heavily use the metax. I mention Magma because I was involved in the implementation of those things, so I know that they exist there. And these are algorithms that are in fact distributed with the system itself. So you may recall that some of the tools that Josh was mentioning yesterday are available on GitHub, part of the TensorSpace site on GitHub. There are some parts of this machinery are also distributed with the system. And this, what I'm talking about below here certainly is. Can I ask you, Alexander, is this machinery, I assume, is also in GAP as well, right? I don't know. I don't know that it is.
Yes, it is. Some of it might be slightly or it might not exactly the same name.
Okay. Yeah. Certainly parts of it will exist anyway, but as I say, I know for a fact these things are available in Magma. So what can we do then? I'm mostly talking here about complexity results, but these are very practical algorithms. It turns out that you can very readily turn into highly efficient pieces of software. But the result basically goes that in polynomial time, if we're given an associative algebra given by generators, we can first of all construct one of these Wedderburn decompositions. Right? You can find the radical and you can split off the semi-simple ring complement. And then you can take this ring complement and basically apply the metax to it. And so Alexander mentioned a little bit earlier that when you apply the metax to things, you can just put it in kind of upper triangular or lower triangular form. Usually you can't necessarily get the direct sum decomposition because it may not exist. But here it does, right? You've got a nice semi-simple algebra kind of acting on this module. You can kind of break it up in a really nice way. You can find these indecomposable summands. And then moreover, when you've got one of these minimal ideals and you've got it acting irreducibly on one of its summands, then it may not be acting as you might say absolutely irreducibly, right? There may be some kind of centralizing ring which is bigger than the field over which you've defined it. But you can calculate that ring. You can do that in various ways. It's one of the ways is given to you by the metax, in fact, immediately. And then you can write the entire module over that ring of this bigger field extension. And then that gives you an effective isomorphism from your minimal ideal to the full matrix algebra over this field extension. And this is a process that we tend to refer to as constructive recognition. You heard this word a little bit earlier today too, in the context of groups. But it kind of applies here too, right? We kind of know what this algebra is isomorphic to. And this is giving us a means of simply writing an isomorphism from your minimal ideal to this very concrete copy of what it is. And this gives us the ability, you see, to, if we're trying to solve problems, which we will be a bit later on, if you're trying to actually solve problems using these decompositions, what you want to be able to do is simply write down the answer that you want and then pull it back to the algebra. And these kinds of algorithms enable you to do that. I just made a remark at the bottom here that that's pretty much all we need for the purposes of today. But next time we're going to need a little bit more from the representation theory of these algebras. In particular, we'll need to talk about things called isotypic components. Right? We'll need to actually know how these minimal ideals are acting on the module.
Could you give a sense for dimensions that you consider tractable?
Oh yeah. So the question James just asked is what is tractable in practice? I don't know for sure, but I certainly just kind of going off memory of things that we've tried to do with star algebras, which we'll come to a little bit later today, that kind of uses all of the same machinery underlying it. My memory is that you can certainly get up to about dimension 80 or 100 or so. The field is somewhat irrelevant. But when you're trying to solve linear equations, and of course those linear equations are not necessarily d cubed type linear equations. sometimes. I think it's roughly d cubed, isn't it? But yeah, so the point is, as the dimension grows, the performance drops off a little bit. But I think you can get up to dimension 80 or 100 fairly readily. The finite field size doesn't matter a great deal. You can let that grow quite well. So that's more or less what I remember, yeah. I've not really experimented with this stuff in a little while, but yeah, it was quite effective though, right? So things that you're going to run into in practice, things that you might want to compute with, there's a pretty good chance that this machinery is good enough, it's powerful enough to be able to help you. Good? All right. So let's have a look at some first applications then. So you may recall that one of the guiding objects that we're trying to work with here is this guy, right? What I've called the autotopism group, or if you want to just call it the automorphism group of the tensor, that's perfectly fine. It's this, it's defined by this equation. And as I've tried to mention or tried to convince you, this is a rather difficult thing to access. It's not an easy thing to compute. And what I want to focus on today on this slide is something that's associated to a different polynomial where we just get rid of the x0 and turn it into a 1. So this is basically, it's the same defining equations as for the autotopism group, except you've just got the identity in the third coordinate. Okay. And it turns out that this changes everything, right? It turns out if you just kind of stare at these equations for a while, you realize that something is in this kind of, oh, by the way, we call this thing the principal autotopism group, or we called it that. For the purposes of today, I've kind of used this notation aut sub 0 just to kind of point to the fact that it's the 0 coordinate that the identity is being induced on here. But if you stare at the defining equations, you realize that something belongs to this aut 0 group. It's a principal autotopism if and only if this thing here, phi 2, phi 1 inverse, belongs to the adjoint algebra. So what does this mean? Well, basically it means that this group is isomorphic to the adjoint, the group of units of the adjoint algebra. And so what we really need to be able to do is to compute the group of units of the adjoint algebra. Okay. Now this, of course, is an interesting problem in its own right. If you're given an algebra A, how can you write down its group of units? And it turns out you can use that structure that I just explained, the radical semi-simple decomposition, the constructive recognition of all of the minimal ideals. You can use that to very good effect simply to write down, not even compute, I mean literally write down. So going back to what Alexander was talking about earlier, I think the paradigm, was it Alexander, the three different things you had in your paradigm where you've got write things down, do things by linear algebra, or it's really hard. Which, I couldn't agree more with, and we'll get onto this a little bit later in the next lecture. But what we're talking about here is having used linear algebra to access the structure of the ring. To write down the group of units literally is writing it down now, right? So you write down the GLs for each of the different matrix algebras that you constructively recognized. This is something that's kind of stored in Magma or GAP or whatever. You can just write down your favorite two generators, pull them back. And then writing down the radical is easy as well. So we've computed the radical. We can even kind of trim the generating set for this radical if we want to, but you can just take a basis for the radical, add the identity to it, and that gives you all of the units of this unit group, if you like, or this group of units. So this was a result that was certainly present in Ronyai's work that I alluded to earlier, in joint work with Eamon O'Brien, going back about 10, 12 years ago. We basically used some of the METAX ideas to kind of make this kind of practical and implemented it. So this is something that is distributed with the Magma system. And we can use it in this context very nicely to simply write down now for a given bimap, we can just simply write down generators for aut 0 of t. And so you'll notice that the answer is coming out here actually as generators, right? So it's in a fairly compact form, the answer to this thing. Okay. I think what I want to talk about now is symmetry. Is that right? Yes. So in Josh Groshow's talk yesterday, he very briefly mentioned this thing called the Baire correspondence. So some of the tensors that you are confronted with in practice, some of the things that you care about, they come equipped with an additional kind of symmetry. Okay. So in this particular case, if you've got let's say a group G, which is a P group, so this is an exponent P, where P is a prime, or exponent 4, as we mentioned yesterday. But we'll just say that P is odd here for the sake of argument. And it's a class 2P group of exponent P. And then corresponding to this thing, we have a bimap which is defined on G mod its center, from G mod its center, cross G mod its center, to the commutator group. Okay? So the thing I want you to notice here is that the symmetry present in quite a lot of ways here. The first one being, of course, that the two domain spaces are identical here, right? And also, if you're interested in automorphisms, which I'll get to in a second, then those automorphisms are going to act in exactly the same way on each of those coordinates, right? So there's this additional symmetry that you're kind of imposing from the problems that you're trying to solve. Furthermore, here we have this alternating property, as we know, right? So if you take a commutator of an element with itself, you're going to get 0. Well, we get the identity, but it's going to be 0 in our vector space. And so it has this alternating property as well. So this is an example of a bimap with inherently symmetric qualities to it, and the problems that we want to solve are also have some kind of symmetry to them as well, right? We can't act independently in each of these coordinates. We have to act in the same way. And that complicates things, it turns out. And we have to be able to handle that in a different way than we've been doing so far. Okay, I mentioned alternating here, and this is something that comes up in the context of P groups, but you could imagine that there may be other situations where you're dealing with a symmetric bimap rather than an alternating one, or it could have some twist of an automorphism as well when you kind of reverse the coordinates. And so to try to capture some of the things that you might be interested in, we make the following definition, that a bimap is going to be called Hermitian if we can find a twisting element of the codomain, a theta in the codomain, a GL of the codomain, that has this property that when you switch the two coordinates, you apply this twisting thing here. Okay. So in particular, when theta is the identity, this kind of captures symmetric bimaps. When theta is minus the identity, it captures the alternating bimaps, and so on and so forth. But it's obviously quite a bit more general. Okay, so what happens here then? So remember that we're dealing with full non-degenerate bimaps, and the full property here, it turns out, dictates that the square of this twisting element has to be 1, right? It has to have order at most 2. And that has some consequences. So if you have an element of your adjoint ring, omega 2, omega 1, remember that omega 2 typically acts in the, I've left the subscript on here because omega 2 actually acts on the first of those coordinates, right? Omega 1 acts on the second. At the beginning of this equation, I'm having omega 1 act on the first coordinate. And then I'm just going to trace through using properties of Hermitian, the fact that theta squared is equal to 1, and then Hermitian again. And what you see is that omega 2 comma omega 1, is also, oh, sorry, I did have it right the first time. Omega 1, omega 2 is also going to be an adjoint of this bimap. Now again, remember that T is a non-degenerate map here, so in a similar way to what happened with the centroid ring, if you restrict to one of the codomain modules, V, then you get a faithful representation of the adjoint ring. And if you simply assign omega 2 star to be omega 1, then what you end up with is something that has obviously order 2. If you do it twice, you get back to where you started. It has an order at most 2, I should say. But it's also not quite an automorphism, it's an anti-automorphism. And this is because of the presence of the star, the op, I should say, in the adjoint ring. So what we end up getting is what we call an involution on the ring. And again, I'm sure some people in the audience have seen these kinds of things before. We have an associative ring, but we also have this anti-automorphism or involution of order at most 2 acting on the ring. And so this is nice. It gives us some additional structure that we didn't have before. But it also means that we have to deal with that structure as well, right? So computationally, if you want to use this, if you want to get the maximum out of this, you have to work with this algebra, AlgT, not just as an associative algebra, but also as a star algebra, what we call a star algebra. Okay, so I'm doing okay on time, I think. So let's have a look at how we do that. So this slide is rather similar in nature to the slide that I had up a little bit earlier, kind of talking about the Wedderburn-Artin theory of associative algebras. This is also a classical theory that was developed sort of around the mid-20th century. If you remember a little bit earlier, I mentioned that the Jacobson radical is defined to be the intersection of all left ideals, and it's also defined to be the intersection of all right ideals. And it turns out that the involution, not surprisingly, interchanges those two sets. It takes left ideals to right ideals. And so what that means is that the intersection of both of these sets is going to be therefore star invariant, right? So it's an invariance of this involution. So that's good. Instead of just an ideal, we've got a star ideal, a star invariant ideal. Now, if we take one of these Wedderburn decompositions, we've got this kind of nice ring theory complement to the radical, but there's absolutely no reason to suppose that if you apply the involution to that complement, you're going to remain where you are, right? It may not be a star invariant complement. However, under a mild condition, you might say, if the characteristic of the field is odd, if you're not talking about characteristic two fields here, then you can indeed find one of these Wedderburn complements that's also star invariant. Okay? So we call such a thing, we can find such a thing, and we're going to call it a Taft decomposition of the star algebra. Okay, so that's good. And remember what we did last time when we got to this stage, we took the semi-simple complement, and then we further decomposed it into minimal ideals. Okay. Now, if we do the same thing again here and kind of forget about the fact that it's a star algebra for a second, if we decompose it into minimal ideals, once again, there's no particular reason to suppose that if you apply the star to those minimal ideals, they're going to stay where they are. It turns out mostly they do, but there is this one odd exception where two different minimal ideals get interchanged by the involution. So it turns out that the classification of simple star rings is not that difficult, actually, but it's a little bit more complex than the Artin-Wedderburn theory, where you were just dealing with a matrix algebra over an extension field. So here what we have is still the matrix algebra over an extension field, but you can have this so-called exchange kind of involution that kind of interchanges two of these things. And then also, of course, what the star does on those simple factors is important, and you kind of have to keep track of that and try to classify it as well. So what can actually happen? And it turns out that the star is going to be induced by a classical form, and those classical forms kind of come in three varieties. We've got some alternating forms, symmetric forms, and emission forms. So they're basically the only four kinds of simple star algebras that you can get. And once again, you can try to constructively recognize those things, and there are algorithms indeed to do precisely that. So the theorem at the bottom is kind of capturing all of that information, that if you're given a star algebra in polynomial time, you can first of all calculate a Taft decomposition. So find this kind of star invariant ring theoretic complement to the radical. You can decompose it into minimal ideals, minimal star ideals, and you can also say exactly what those star ideals are. You can constructively recognize them, build the classical form that induces the star. And so you're once again in a situation where problems that you want to solve about that star ring, you can more or less just write down the answer to and then pull it back to your algebra. So with that in mind, let's just have a look at another example. Or maybe I'll give you an example, first of all, of a P group that sort of, and tell you what these adjoints and centroids look like. So this is something called a generalized Heisenberg group. Again, this may be a familiar object to people in the audience. It's something we'll again come back to in the second talk on Friday. So the idea is that it's quite a simple thing to define. It's a simple thing to look at. you take an extension of a prime field, so just our favorite field F of Q elements, and you take an integer m, and we're going to build this, I guess, m plus 2 dimensional matrix with the m by m identity matrix in the middle. We're going to take 2 vectors in f to the m. One of them is going to be a row vector, the other one we're going to transpose and put on as a column vector. And then take any scalar in the field S. And if we do that little bare correspondence trick that we did earlier, we end up with a bimap, an alternating bimap from G mod Z to from G mod Z into G prime. And again, if you calculate these different objects that we've mentioned today, the centroid turns out to be isomorphic just to the field of scalars. And in fact, if you rewrite the, I should mention that when you write this bimap, this is going to come out to P group, right? So it's going to come out to be not necessarily an m by m form in its natural state. It's going to be, whatever the degree of the extension is, it's going to be kind of blown up. It's going to be sort of unnatural. But 2m, sorry, yeah. I do mean 2m, sorry, yeah. Yeah, James, the question is, do I mean 2m here? And I do, of course, mean a 2m dimensional vector space. So we get this alternating form from f to the 2m, cross f to the 2m to f. So that's what happens if you write it over the centroid. And if you calculate the adjoint ring, it turns out that what you get is the full matrix algebra, right? So this is quite a hefty adjoint algebra that we get here. We get the entire algebra of matrices, and the involution is going to be induced by the form that we had. So it's an alternating type. So this would be one of those simple star rings that we mentioned in the previous slide. Good. So I'm doing okay on time, I think. Let me just talk about an application that kind of mirrors the application that we saw a little bit earlier. So again, if you remember that in this context, if we're given this theta emission bimap, the applications that we're kind of interested in sort of demand that we act on these 2 coordinates in exactly the same way, right? And so the group that kind of corresponds to the autotopism group or the automorphism group is something that we call pseudo-isometry. And you may remember a joke from Josh yesterday about this pseudo-isometry group, you know, this well-established piece of terminology which James apparently made up.
You got the pitchfork, right?
Yeah, that's right. So my contribution to this was, if you try to draw this in tech, the pitchfork and the isom are really too far away from each other. And so it's quite a stellar contribution of mine, but really what I did was I did something like an H space star minus 0.2 millimeters and brought those things closer together again. You're welcome. It's okay. Yeah. So we end up with this group. This is the group of interest. And again, this is a very difficult thing to calculate, right? This is the hard problem, the corresponding hard problem in this context. So what's the analog of the principal autotopism group? Remember in that example from a few slides ago, we said, well, what happens if you just kind of act as the identity on the outer coordinate? What can you do then? And of course, you're very familiar. I mean, I'm sure everybody in this room is very familiar with what this equation looks like. This is the familiar isometry equation, right? Which is where the pseudo-isometry came from. So you're simply asking here that if you apply the invertible map to each of these coordinates and apply the tensor to it, then the answer doesn't change. It's just isometry in the usual sense. So can we, just like we could with principal isotopism, can we build this group? And it turns out we can, but it's a little bit more complicated. It's not quite as simple as writing down the answer, but it's close after you do a lot of work. So what's involved here? So remember, in the background, we've got this adjoint algebra now, which is a star algebra, okay? In the principal isotopism world, what we did was we wrote down the group of units. That was the correct group, it turned out. That was exactly the principal isotopism group. Here, what we want to write down is not the group of units, but rather the unitary group. So things where if you apply the star to an element and then multiply by the element, you end up with the identity, okay? So it's a little bit of a different group that you're trying to find, but it turns out it's almost as easy to find it. You have to be a little bit careful with the radical, it turns out. So the characteristic being odd is extremely important there as well. You have to do something a little bit clever with the radical. But writing down the unitary elements of the semi-simple part is extremely easy. So again, you've got this adjoint algebra with a particular form attached to it, and the unitary elements kind of correspond to just the isometries of the form. So it could be a symplectic group, it could be an orthogonal group, it could be a unitary group, that's it. In the case of the exchange one, you're just going to get a single copy of GL. Right? So it's actually quite easy to write down these unitary elements, and again, pull back your answer, and then this gives you generators for this isometry group. Now this particular theorem has a very special place in my heart, because this was sort of where the theorem where James and I sort of first started talking to each other about these kinds of problems. And I just want to kind of mention the problem that I was working on when we came to this. I'd just been down to visit Eamon O'Brien in Auckland, and he was kind of interested in, for P group reasons it turns out, he was interested in the problem of taking a collection of symplectic groups defined on a common module, right? So they preserve different forms, but they're all symplectic groups. They're all isometries of some alternating form on a fixed vector space. And what he wanted to do was to kind of intersect those things, right? So he wanted to find the group intersecting the intersection of all of those different symplectic groups. And of course, we didn't succeed very well. We succeeded in working with two of these groups. We were able to work with pairs of other classical groups, like pairs of orthogonal groups, pairs of unitary groups. And then we had some sort of ad hoc ways of trying to generalize this. And then I came back from New Zealand to Oregon, where James was just finishing up his PhD, and told him this problem, and he goes, well, you're doing it all wrong, basically. That's sort of how the conversation went. And rather than think about these things as like a sequence of forms, now remember that this is one of the data structures that we've been using, right? If you want to describe a bimap, what have we been doing? We've been giving you kind of sequences of forms. In the literature, these things are called systems of forms, and people have worked with them a lot. But James's viewpoint was, well, you shouldn't really be working with them as systems of forms. You should be thinking of this as a single bimap, right? And then so that's where this particular avenue kind of was born, and we realized that you can actually write down the intersection of all classical groups, any collection of classical groups you want, any number of forms. If you regard it as a bilinear map, you can simply write down the isometry group and bang, you've solved your problem. So it's really quite nice. I should also mention from Alexander's talk, you may recall as well that the the famous Ashbacher result, talks about 9 different categories of possibilities for matrix groups, right? It turns out that one of those possibilities for matrix groups is classical groups defined in their natural representation, okay? And so there's obviously 8 others of those. And so I think when we first announced this result, Charles Leadham Green was in the audience, and he said, well, that's good, you solved 1/81st of the intersection problems of maximal subgroups, right? So now that you've described all the maximal subgroups, you want to describe intersections of maximal subgroups. We've solved 1/81st of that. So, but it's something, isn't it? It's non-zero. So. One last thing, which is going to be important next time. So the time that we started working with Josh Groschow a little while ago and Yuming Chow, we had this discussion where Yuming was kind of telling us about a result that he proved with Gabor Ivanios that was very similar to the one that we'd proved here, but it was really to do with 2 different alternating bimaps, right? If you're given 2 different alternating bimaps, an S and a T, can you decide whether they're isometric, right? Is there an isometry between them? And I suppose, looking back on it, we were just not really tuned into that problem at all. I mean, we were focused so much on the group, James and I, we didn't particularly think about the problem, or really what its impact might be, what the repercussions of solving that problem might be. And so when Yuming told us about this result, we're like, well, that's really clever, it's good, we're using our result, but so what? Yeah. I think it was actually after James had left and the 3 of us were kind of wandering around a mountain somewhere in San